Welcome to this comprehensive guide to LeetCode Problem number 621, Task Scheduler. In this lesson, we will break down the problem in detail, analyze multiple approaches, and provide step-by-step walkthroughs with examples. We will also dive deep into algorithmic strategies, present implementations in both Python and Java, and discuss complexity analyses, tips, and common interview scenarios. By the end of this video, you will not only understand how to solve LeetCode Problem number 621 optimally, but also why its greedy scheduling approach is so powerful. Let's get started and master both Python and Java solutions together. LeetCode Problem number 621 asks you to schedule a list of tasks so that the same type of task will be separated by at least n units of time due to CPU cooldown. Each task takes exactly one time unit. You may need to insert idle periods if you cannot schedule any available tasks due to cooldown constraints. The goal is to find the minimum total time to finish all tasks. Let's walk through each example provided by LeetCode and explain how the constraints impact task scheduling. In the first example, tasks are 3 A's and 3 B's, with cooldown n equal to 2. The optimal schedule is A, B, idle, A, B, idle, A, B, totaling 8 units of time. In the second example, there is no cooldown, so you can schedule tasks directly, finishing in 6 units of time, just the task count. In the third, the frequent task forces idle slots since its occurrences exceed the others. Constraints are straightforward, up to 10,000 tasks, each is a letter, and n can be up to 100. Edge cases include n equals 0, all tasks unique, and a single task with high frequency, which may maximize required idle slots. In the next slide, we'll continue with more illustrative examples and deep dive into how the schedule is constructed. Continuing with further examples, consider when all tasks are unique, such as A, B, C, D, E, F with n equal to 2. Since there are no repeats, you simply schedule all tasks back-to-back, yielding the output 6. For the case of 3 A's and n equals 3, idle slots are required between A's, and the minimum schedule becomes A, idle, 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 A, idle, 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 A. Therefore, total units consumed equals 7. Other critical edge cases include when all tasks are identical with n larger than 1, pushing idle time up to maximize CPU waiting periods. If n exceeds number of distinct tasks, less idle time is needed, as lower frequency tasks can occupy idle slots. For a single task input regardless of n, only 1 unit is needed. If n is large but tasks are all unique, you still only require as many units as tasks available. These examples illustrate the paramount role frequency and cooldown play in constructing the optimal schedule in LeetCode Problem number 621. There are 2 classic approaches for LeetCode Problem number 621. The first is simulation, using a priority queue to repeatedly schedule the most frequent remaining task. Idle slots and cooldowns are tracked until all tasks are finished. Although conceptually clear, this approach can be slow for very large inputs. The second is a greedy mathematical formula. Here, we focus on the task type that appears most frequently, and design the schedule so that these high-frequency tasks are distributed with at least n units between identical types. The minimum time required is calculated with max frequency minus 1 times n plus 1, plus the number of tasks that have that maximum frequency. This spreads out the critical tasks and fills in the rest with remaining task types. When the total number of tasks is higher than the computed minimum, the output is just the task count because extra tasks fill idle slots automatically. For LeetCode Problem number 621, the greedy method is optimal and preferred for its speed and simplicity. Let's look deeper into how this works. For LeetCode Problem number 621, the step-by-step greedy algorithm begins by counting the frequency of each task letter. Next, we identify the highest frequency and count how many task types share this maximum. To minimize idle periods, we lay out the schedule in blocks. For every occurrence except the last, we need to separate with a block of n plus 1 units. Inside each block, fill with other tasks before idling. If there are more tasks than what the formula predicts, excess tasks fill up idle slots, so total time equals the number of tasks. This approach leverages frequency analysis and block scheduling for optimal efficiency. Let's walk through the Python solution for LeetCode problem number 621. We first create an array of size 26 to record how many times each task appears. Then, we scan this array for the highest frequency. We also find how many distinct tasks reach that highest count. The schedule is built from blocks, the most frequent tasks spread across blocks of size n+1. The minimum time is the product of blocks and block length, with additional slots for tasks sharing the maximum frequency. If there are more tasks than idle slots, result is simply total tasks. This solution is concise, clear, and runs in linear time. Here is the Java equivalent for LeetCode problem number 621. The logic is the same as in Python, but uses Java syntax and structure. We iterate through the task array, count frequencies with an array of size 26, then calculate the maximum frequency and its count. Java requires explicit types and uses math.max for the final step. Both implementations run with the same efficiency and structure, with Java being more verbose due to its static typing and class layout. Let's thoroughly walk through several examples for LeetCode problem number 621. For the first case, 3 A's and 3 B's, with n equals 2, we count frequencies and see both A and B appear 3 times. We build 2 blocks of 3 units, then add in final tasks. The resulting schedule is A, B, idle, A, B, idle, A, B, totaling 8 units. For n equals 0, you simply schedule every task. Output is the length of the task list, 6. In the next example, there are 4 A's and 2 each of B and C, with n equals 2. Here, idle slots are forced, so minimum time is calculated as 3 blocks, 3 units each, plus 1 for the last A, total 10 units. The greedy formula automates this analysis. In LeetCode problem number 621, the greedy method is ideal. Frequency counting of tasks is linear in time. All other steps use a fixed size array of 26 elements, making them constant time and space. In contrast, simulation methods with priority queues have overhead. Hence, greedy formula-based calculation is preferred for high performance and efficiency on large input sizes. This makes our solution robust for interviews and production use. For LeetCode problem number 621 and similar scheduling tasks, remember that optimal solutions rely on understanding the impact of frequency on idle periods. Be wary of mistakes, such as missing cases with multiple max frequency tasks or miscalculating required idle slots. Using simple arrays is efficient both in code and memory. Always highlight in interviews why the greedy approach is optimal and how priority queues, while instructive, can add unnecessary complexity. Reviewing related LeetCode problems can extend your mastery over a broad range of scheduling and reordering problems. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!